Hello and welcome to the next topic under the heading of deadlocks. We will be discussing about how to handle deadlocks and what a safe state and unsafe state is. We can deal with the deadlock problem in one of the three ways. We can use a protocol to prevent or avoid deadlock, ensuring that the system will never enter a deadlock state. We can allow the system to enter into a deadlock state and detect it and then recover. And in the last, we can ignore the problem altogether and pretend that the deadlocks never occur in the system. The prevention provides a set of methods, a set of techniques for ensuring that at least one of the necessary conditions cannot hold. What necessary conditions? Earlier we have studied mutual exclusion, hold and wait, no preemption, circular wait. These conditions we try to break by using prevention techniques. Deadlock avoidance requires that the operating system be given in advance some additional information concerning the resources a process will request and during its lifetime what it may request in future also. With this additional knowledge, it can decide for each request whether it should or not process the request. To decide whether the current request can be satisfied, a system must consider the resources currently available, the resources currently allocated to each process, and future requests and releases by the process. Now we will discuss deadlock prevention technique. Earlier we used to have 4 situations simultaneously which can lead to a deadlock situation. In order to break the mutual exclusion situation, the mutual exclusion condition must hold for non-shareable resources first of all. For example, a printer cannot be simultaneously shared by several processes. In case of shareable resources, they do not require mutually exclusive access and thus cannot be involved in a deadlock. For example, read-only files are a very good example of shareable resources. If several processes attempts to open a read-only file at a time, they are granted simultaneous access. The process never needs to wait for a shareable resource. Hence, the mutual exclusion can be stopped here. Next is the hold and wait. In this condition, what earlier used to happen, a process hold a resource and wait for another resource to be occupied. If it was not given the resource which the process was asking for, then the process was asked to wait, holding another resource. Now we must guarantee that whenever a process requests a resource, it does not hold any other resource. This is how hold await condition can be broke. One technique can be used that each process to request and be allocated all its resources before it begins the execution. Another technique says allow a process to request a resource only when a process has none allocated to it. Which means a process may request some resources and use them. Before it can request any additional resource, it must release all the resources that is currently allocated to it. Both these two protocols has two main disadvantages. First disadvantage is low resource utilization, since resources may be allocated but they are not being used for a long time. And the second problem is that starvation can be possible. For example, a process that needs several popular resources may have to wait indefinitely because at least one of the resources that it needs is always allocated to some other process. Third condition which we have to break is of no preemption technique. In this, if a process is holding some resources and requests another resource that cannot be immediately allocated to it, then all the resources the process is currently holding are preempted, are removed or taken back or are released from the process. Preemptive resources which are released from the process, which are taken back from the process, are added to the list of resources for which the processes are waiting. A process will be restarted only when it can regain its old resources as well as the new one that it is requesting. Alternatively, if a process requests some resources, we first check whether they are available. If they are, we allocate them. If they are not, we check whether they are allocated to some other process that is waiting for additional resources. If so, we preempt the desired resources from the waiting process and allocate them to the requesting process. If the resources are neither available nor held by a waiting process, the requesting process must wait. And the last condition which we have to break is about circular wait. You are right now looking at a diagram which is explaining circular wait. What is happening here is that a deadlock has occurred according to the diagram. Because PA is holding resource R1 and also requesting for R2, the process PB is holding request R2 and is requesting for R1, and the resources are having only one instance. Hence, the processes PA and PB are in circular wait. The table is shown on the right hand side of diagram, which is saying that PA is having R1 resource and is waiting for R2, and PB is holding the resource R2 and is waiting for resource R1 to get free. Now, the circular wait technique can be broken, condition can be broken if we assign each resource type a unique integer number, which allows us to compare two resources and determine whether one precedes another in our ordering or not. Now, on the screen, the table which has been drawn just below the diagram, it says that PA and PB will both compete for R1 first, since a unique integer has been given and an ordering is required for allocation of the resources in order to break the circular wait condition. Now, PA and PB will both compete for resource R1 first. If PA gets R1, then PB will not acquire R2. This means that R2 will be free for PA, and after using R1 by the PA, it will free resource R1 for PB. Then PB will use R1 at that time. PA will be using R2 to complete itself. Hence, there is no circular wait. Now, under deadlock avoidance, a pre-knowledge of complete sequence of resources and releases for each process is to be known. For example, in a system with one tape drive and one printer, the system might need to know that process P will request first the tape drive and then the printer before releasing the resource. Whereas process Q will request first printer and then the tape drive. This knowledge of complete sequence of request and releases of each process, the system can decide for each request whether or not to process. Simplest and most useful model requires that each process must declare maximum number of resources of each type that it may need. Safe state. It is basically the sequence in which the processes will be executed. A state is safe if the system can allocate the resources to each of the process in some order and still avoid a deadlock. More formally, the system is in safe state only if there exists a safe sequence. A sequence of processes is a safe sequence for the current allocation state. if for each process pi can be p1, p2, p3, the resource request that pi make can be satisfied by the currently available resources plus the resources which are held by all other processes, which are called pj. When a process pi terminates, then the next process, which is pi plus 1, can obtain its needed resources and the execution can go further. Now, based on the diagram on the screen, if a list of processes are executed and the system is in safe state, then there is no deadlock. But a deadlock state comes in an unsafe state. Based on the diagram, not all unsafe states are deadlock. An unsafe state may lead to a deadlock. Let's see how. Now, total magnetic tapes which are with the system are 12. I am having three processes, process P0, P1 and P2. Process P0 require maximum 10 tape drives, P0 requires maximum 10 tape drives, P1 require maximum 4 tape drives, P2 require maximum 9 tape drives. At current situation, P0 has been allotted 5 tape drives and it is waiting for 5 more. P1 has been acquired P1 has been acquired 2 tape drives and it is also waiting for 2 more tape drives. P2 has been acquired 2 tape drives and it is waiting for 7 tape drives. Right now P0, P1 and P2 can ask or may ask for the more tape drives. 5 to 2 has been allocated and 5 to 7 are the further requirement. Now, since we see that total number of tape drives are 12 and out of which 5 plus 2 plus 2, which is 9, has been allocated, so 3 are remaining with the system. Now, a safe sequence has been given that first of all execute process P1, then execute process P0 and then execute process P2. What happens if we execute process P1 first? Since P1 requires 2 more tape drives, hence it is given the 2 tape drives. Now process P1 can be immediately allocated all its tape drives. After allocation, it will return them and the system will have 5 available tape drives now. Then, based on the sequence, the process P0 can get all its tape drive and return them. Now, the system will have 10 tape drives. And based on the sequence, finally, P2 requires 7 more tape drives. P2 can get all its tape drive and return them. The system will have then all the 12 tape drives available with it. So this will make an execution of 3 processes based on the resources available by the system in a very safe and smooth way. Now let's make a small change in the current holding situation. Now suppose at time t1 process P2 requests and is allocated 1 more tape drive. If we look at process P2 currently holding status, it is holding 3 tape drives, which means the free tape drives available with the system is 2 now. Now if we follow the safe sequence of P1, P0 and P2, let's see what happens. The system will no longer be in the safe state. At this point, only P1 can be allocated all its tape drives. When it returns them, the system will have only 4 available tape drives. Since process P0 is allocated 5 drives, but it has maximum requirement of 10. It may request 5 more tape drives. If it does so, it will have to wait because system is having only 4 tape drives because they are unavailable. Similarly, process P2 may request 6 additional tape drives and they have to wait also. So this will result in a deadlock. Our mistake was granting the request from process P2 just 1 extra tape drive. If we have made P2 wait, either of the other processes must have finished, released its resources, then we could have avoided the deadlock in this current scenario. So this finishes our session for today. Thank you very much for attending.